explainer. Today, we're going on a tour inside your own body. We're going to uncover the brilliant and honestly kind of overlooked engineering of your knee joint. It is a total masterpiece of biomechanics, and trust me, by the end of this, you are going to see exactly what makes it so special. So, let's just jump right in with a question you can literally test out right now. Seriously, go for it. If you're sitting down, just straighten your leg and try to wiggle your lower leg side to side. See? It's not going anywhere, right? It's pretty much rock solid. Now bend your knee to about 90 degrees and try that same wiggle. Whoa, suddenly it's got all this play, this wobble. So what's the deal with that? Well, the secret to your knee's kind of split personality, being super stable one second and mobile the next, it all becomes clear when we compare it to another joint you know really well, the knuckle in your finger. It's fascinating, because they solve the exact same problem of stability in completely opposite ways. Okay, first things first, let's set a baseline by looking at something a bit simpler, the design of your finger's knuckle joint. The metacarpophalangeal joint, or MCP joint. Yeah, let's just call it the knuckle. So, take a look here. On the left, that's a CT scan showing you the actual bones in your knuckle. And over on the right, we've got a simplified diagram. See those bands? Those are the collateral ligaments. They're the key stabilizers that run along the sides of the joint. The important thing to notice is how they're lined up. Okay, so the real key to how your finger works is the shape of the bone itself. The end of that bone, the metacarpal, is almost a perfect circle. Think of it like a simple, smooth hinge. The technical term for this is a constant radius of curvature. And believe me, that simple shape is everything when it comes to how this joint works. So when you look at it, the finger's design is just, it's elegantly simple. You've got that constant predictable curve on the bone, and the ligaments on each side, they just run parallel to each other. They never cross. This whole setup is designed to give you what we call active, non-locking stability. And here's the crucial part. When you make a fist, right? When you bend your finger, a wider part of that round bone actually rolls under the ligaments. This stretches them out, pulls everything tight, and gives you a super stable grip. But, and this is a big but, it takes muscle power to keep it tight. This is stability for doing something, for actively grabbing onto things. All right, now let's switch gears and head over to the knee. You're about to see a completely different, and honestly, a way more complex system. This is no simple hinge, not by a long shot. So just like we did with the finger, we've got the real deal on the left and a diagram on the right. But I want you to look really closely. You can see right away that the shape of the femur, your thigh bone, is way more complicated. And check out the ligaments. They are definitely not running parallel anymore, are they? Yeah, so unlike that simple round finger bone, the end of the femur has what's called a variable radius of curvature. It's not a perfect circle at all. The curve is actually changing constantly along its surface. You can almost think of the bone ends as a pair of cleverly designed wedges that interact as the joint moves. And this is where the genius really kicks in. This design combines that weird, variable bone shape with ligaments that run in opposite slanted directions. And here's the really wild part. They actually cross each other in space. This unique geometry is the entire secret to the knee's passive locking stability. So, what does all this geometry mean? Well, it means the knee's mechanics are basically the exact opposite of the fingers. They become stable at totally different times. This table just lays it all out, nice and simple. Finger, constant curve, parallel ligaments, tightens when you bend it. Knee, variable curve, intersecting ligaments, tightens when you straighten it. It's a total reversal. And this gets right to the why of it all. It shows you the purpose behind each design. The finger is built for an active job, gripping things. But the knee, it's engineered for something completely passive, just standing there without any effort. So just to hammer it home, the finger gets stable when you bend it, perfect for grabbing and holding on. But the knee, it gets tight and stable when you straighten it. And that brings us right back to where we started. That rock-solid feeling when your leg is straight, that's it. That's the ligaments being stretched tight purely by the shape of your bones. And the implication here is, it's huge. Making your finger stable takes muscle work. But keeping your knee stable when you're just standing around, it's completely passive. It's effortless. It's all thanks to this incredible design. It's not biology at that point. It's just pure physics. But wait, there's more. Seriously, to get that ultimate, unshakable stability, the knee has one final, really elegant trick it pulls.
Right as your knee gets all the way straight, the femur makes this tiny little inward twist on your shin bone. It's a very small movement, but it's called the terminal locking mechanism, or sometimes the screw home mechanism. And that little twist, it massively cranks up the tension on the ligaments.
And this one little locking move is so effective because it triggers two really powerful stabilizing effects at the exact same time. Okay, so first, that little twist stretches and tightens both of those side ligaments even more. It's kind of like turning a key to fully engage a lock. And second, it creates something amazing called the sling-like effect. So remember how those ligaments cross each other? Well, when that final twist pulls them both super tight, their forces combine. They literally form a rigid, passive sling that braces the joint and resists force from pretty much any direction. And the best part? It happens without you having to fire a single muscle. And this image here shows that sling perfectly. You can see how those crossing bands, representing the ligaments, create this incredibly strong, stable structure. That is the secret. That's how you can stand for hours without your knees just giving out and without your leg muscles burning out from the effort. So when you think about it, the wobbly knee is for motion, for walking, running, all the dynamic stuff. But the locked knee? That's for effortless, super efficient stability. It's just amazing, isn't it?